Hello, welcome back. Fasten your seatbelts. We have so many things to do today. So let's review basically the Radix 2 Decimation-in-time FFT. So basically we can efficiently implement the discrete Fourier transform by this idea, this recursive idea in which like you compute the n over 2 DFT of the even samples, so those are x of 0, x of 2, and so on, and then the n over 2 DFT of the odd samples, which is x of 1, x of 3, and so on. And then you can basically combine the outputs to obtain the endpoint DFT. And basically what you need to do are basically n over 2 multiplications, because those guys must be multiplied by the twiddle factors. And then we need to have basically n additions. Okay, so those minus signs here will also be considered as additions from a complexity point of view. So we have basically, so to combine, to merge the results, we have n additions and n over 2 multiplications by the twiddle factors. Okay, and then how can actually we obtain those guys? So basically you repeat the same idea. You take those those input samples, you divide them into even and odd, and you keep doing this till you get 2-point DFTs. 2-point DFTs are very straightforward. Basically, the first output is the sum of the two samples, and the second output is the difference between the two samples. And basically, the overall complexity will be n log n to the base 2 additions, n over 2 log n to the base 2 multiplications. Okay, and the combining step, so the combining step that we do here can be thought of in this way here. So we have the n over 2-point DFT, the n over 2-point DFT. So this is the even, this is the odd. So this is basically the DFT of x of 0, x of 2, x of 4, and so on. And this one is the DFT of x of 1, x of 3, x of 5, and so on. And then you can basically think of what you are doing is that you take the kth output here, the kth output from there, and k is a number between is an integer between 0 and n over 2 minus 1. Remember that big N is a power of 2. And then we multiply basically this by e to the minus I2 by k over n. And then we do a 2-point DFT, right? Because, like, remember what we did last time. You have an upper output, which is the sum, okay, and then a lower output, which is the difference. And what is sum and difference? It's just the 2-point DFT. So this is a nice way of thinking about it, that to produce output x of k and x of k plus n over 2, we apply a 2-point DFT to the kth outputs from these two blocks. Okay, so this is, again, this is nice if we want to extend the idea, because life is not just about numbers that are a power of 2. We have also powers of 3. Okay, and so what if n is a power of 3? Now, if you understand what happened in the previous lecture, you'll find that basically the steps here are straightforward, and you should be able to write them down without looking. Okay, and so this is like a test, whether you got this idea of decimation in time. So we have basically n now is a power of 3, so it is 3 to the power something. And before investigating the endpoint DFT, let's just think about the 3-point DFT. So in the case of Radix 2, basically we talked about the 2-point DFT. The 3-point DFT is a bit more complicated. It has 3 terms in this summation, and you can extend, you can write down the sum in this expanded form as a small x of 0 plus x of 1 e to the I 2 pi k over 3 plus x of 2 e to the I 2 pi k 2 over 3. And then you need to compute this thing for k equals 0, k equals 1, and k equals 2. And so this is basically everything in, explicitly. And, if you count, so basically there are 4 multiplications. So we need to multiply for big X of 1 we need to do this multiplication and that multiplication, and for big X of 2, we need to do that multiplication and that multiplication. So overall, we have 4 multiplications and those 6 additions. Okay, so keep this in mind, that the 3-point DFT, its computational complexity is 6 additions and 4 multiplications. Okay, and how do we know this? Just write down everything explicitly. So write down this summation for the 3 values of k equals 0, k equals 1, k equals 2, and you will see basically the computations that you need to carry out in order to compute the 3-point DFT. So this is if the power of 3 is 1, and you will just do it this way. You will have to do 6 additions, 4 multiplications. But what if we have a general power of 3? So we take our endpoint DFT. Then we split the summation into 3 parts. Okay, so for the 2 points, for the when big N was a power of 2, we basically took x of 0 with x of 2 with x of 4 together, and then x of 1, x of 3, and x of 5 together. Now we will do 3 basically groupings. So we will have x of 0, x of 3, x of 6 together, and then we will have x of 1, x of 4, x of 7 together, and then we will have x of 2, x of 5, x of 8, and so on together. So here the splitting is into 3 groups. Okay, so basically the numbers that you have here are basically the numbers that are 0 modulo 3. Those are the numbers that are 1 modulo 3, and those are the numbers that are 2 modulo 3. So this is the first step. Now the second step, as we did in the previous case of the power of 2, but now you have basically a different change of summation indices. So in this summation, because here those numbers are the multiples of 3, we will use m equal 3n. Those are the numbers that when divided by 3, they give a remainder of 1. So here we will do m is equal to 3n plus 1. And here m is equal to 3n plus 2. And then we change every m in the expression to, in the first summation, m is replaced by 3n, here 3n plus 1, there 3n plus 2. Then from the second and third terms, we will get extra factors, right? Because you will take this guy, you will insert 3n plus 1 over n, and so you will get an extra factor, which is e to the I 2 pi k over big N. And here you will get this extra factor. And then you do the same trick like we did last time, which is, so you have this guy inside the summation. You just say, okay, I will take this 3 and I will put it downstairs. And then each summation, the index will go from 0 to n over 3 minus 1. So if you look at this summation, what is this summation? So this summation is the n over 3 point DFT of x of 0, x of 3, x of 6, and so on. What is the second summation? It is the n over 3 point DFT of x of 1, x of 4, and so on. So now I will call those guys. This one I will call x sub a, this x sub b, and this one x sub c. Okay? And note that each one of those sequences is n over 3 periodic, which means, for example, that if you take this guy and if you replace k by k plus n over 3, or a multiple of n over 3, you will get the same result back. Those are n over 3 point DFTs, and so they are periodic with a period that is equal to big N over 3. Now, if you take this expression, replace k by k plus n over 3, those guys remain unchanged because of this periodicity. But then this k here and this k here will be replaced by k plus n over 3. And so we get extra factors. And the same if we replace k by k plus 2n over 3. And so we look at those 3 expressions together, Okay, so so this guy, this term here. Okay, so let me do it. So this term here is always multiplied by this guy. So it will always appear multiplied by this guy. Okay, the other one is always multiplied by this guy. So those will be like multiplication by twiddle factors. But then there are those terms. And if you look to the 3-point DFT, those are exactly the same terms that we have here. Okay, so what is the conclusion? Here is the conclusion. If you are able to compute the n over 3-point DFTs, so this is of x of 0, x of 3, and so on. This is of x of 1, x of 4, and so on. This one is of x of 2, x of 5, and so on. Now, here is the trick, or here is the procedure to combine the outputs to obtain, the required n-point DFT. So let's focus on the kth output from here, from there, and from there, and let's assume that k is 0, 1, 2, up to n over 3 minus 1. So according to those three lines, which again, nothing mysterious about them, you do them following these steps. What you need to do is to take this guy and multiply by this twiddle factor, take this guy and multiply by this twiddle factor, and then we need to implement something like this, a plus and a plus, a plus and a plus, and then we have those two exponentials, and then here those two exponentials. This is exactly like the 3-point DFT. So we will take the kth output from the first block, the kth output from the second block, the kth output from the third block. We multiply by the twiddle factors. Then we feed the result to a 3-point DFT. And the 3-point DFT will give us the outputs that we are interested in, k plus n over 3 and k plus 2 n over 3. So you will basically, you will sweep over k 0, 1, 2, 3, 4. And for each k value in this set, we will compute 3 outputs. Okay. Now, what is the complexity of merging those results into the required DFT? Well, what is the complexity of this block? 6 additions, 4 multiplications. So we need this to produce 3 outputs. Okay, so to produce 3 outputs. So and before we move, and then we have basically the multiplication by the twiddle factors. So let's compute the total number of additions. There are no additions here, those are multiplications, and then we need 6 additions to produce 3 outputs. 6 additions to produce 3 outputs. So how many additions so 6 additions will give you 3 outputs. So how many additions to get n outputs? To basically 6 times n over 3. So we will need 2 n additions. To do this merging, we take the results from these 3 guys and combine them to produce the outputs. So here we will need to carry out 6 additions to produce 3 outputs. Then we need 6 times n over 3 additions to produce n outputs. And the overall, so basically overall, this merging will require 2 n additions. For multiplications, so we need to multiply 4 by n over 3, but then don't forget that we have multiplication by the twiddle factors. And so basically two-thirds of your data here will be multiplied by twiddle factors. And so we have 2n over 3 multiplications. So here, the first block, it's multiplied by nothing, but those k outputs will be multiplied by this guy, and those k outputs by this guy. So we have an overall of 2n over 3 multiplications by the twiddle factors, so 2n. So this will be per stage. Then you can do something like in the previous lecture, and then you ask yourself, how can I implement this block well, you will repeat the same idea. Okay, and again, if you draw things, if you do things in details, you will find that you need this number of additions and multiplications at each stage, and overall you have log n to the base 3 stages, and so this will be the overall number of additions and multiplications. Again, we have complexity n log n, the magic number that we use, like we have for fast Fourier transforms. In the notes, I will leave you, so please read Radix 4. Okay, it's nice. It's a nice algorithm, and it has some advantage that I wish you will basically get. I mean, so basically the number of multiplications is reduced by exploiting a certain fact that you will see in the notes. Okay, and you can do this. I mean, Radix 5, you will start by splitting your sum into 5 sum and so on. Okay, so you got this idea. So the idea is that you do this splitting, and you combine the results with linear complexity, and then the number of stages is log n to the base 2 or to the base 3 or to the base 5 or 4, whatever. Okay? So, any questions? In some applications, we have n that is a multiple of n1, n2. So suppose that n is 2 to the 10 times 3 to the 12. Okay, so what should we do? So suppose that n can be written as the product n1, n2, and both are integers greater than or equal to 2. And suppose that you already have an efficient algorithm for doing n1 point DFTs and another efficient algorithm for doing n2 point DFTs. So efficient algorithm, we understand now in the context of DFT, it means order n log n. Okay, so suppose that, so in something like this, we already know an algorithm that will deal efficiently with the case in which the number of points or the number of samples is a power of 2. We have another algorithm in which you can handle efficiently the case when n is a power of 3. So what if big N now, the total number of points is of course those numbers are are huge, but just for illustration, you need to handle a situation like this, and the idea here can be extended, right? Because you can apply it to something something like this. 5 to the 5 to the, let's say, 6. Okay, so once you learn this idea, again you can sort of reapply it, and you can now do any DFT of your choice, except when big N is sort of a large prime number. So if a big N is a large prime number, then what should we do? So this will be in your homework. You will do it Rader's algorithm. So this will be your homework 7. Okay, and basically it is sort of the missing piece of the puzzle. Okay, so you can do the powers of small primes, or even if they are not prime, you can do Radix for FFTs. You can basically, if you have a composite number in this form, you can deal with it, as I will explain shortly. What if you have a larger prime? So the missing piece will be this guy, and what do you expect? Order n log n. Okay, it is just the annoying thing is that the FFT, there is no universal FFT algorithm for any size. You need to adapt your algorithm based on the number of samples, basically for which you are trying to compute the DFT. Okay. So now your data, basically your data is n, where n is n1 by n2. You will do something here that is seemingly strange. You will basically think of your data as if it's two-dimensional. So n is n1, n2. Rather than thinking of your data as a vector with n1, n2 elements, you will think of your data as a matrix or a two-dimensional array with basically n1 rows and n2 columns. And you will put your data in this way: x of 0, x of 1, x of 2, up to x of n1 minus 1, x of n1, x of n1 plus 1, x of n1 plus 2, and you keep doing this till you reach the last element, x of n1, n2 minus 1. So now, to index an element in this array, we need two indices. And so basically the idea is that we replace index n by two indices, n1 plus big N1, N2. N1 is from 0 to big N1 minus 1, and N2 is from 0 to big N2 minus 1. Okay, so when N2 is equal to 0, this term is 0, and N1 will go from 0 to n minus 1. And so this will give you the first column here. Now N2 is equal to 1, then now N1, okay, again from 0 to n minus 1, now N1 plus N1, because N2 is equal to 1, will be from N1 to 2, N1 minus 1. So this will give you the second column, and so on and so forth. Strange. So you will take your data, and again, the first step is, it's sort of pre-processing. You arrange your data as a two-dimensional array. And this two-dimensional array, it has two indices, n1 and n2, and they are related to the original index small n. Small n is n1 plus big N1, N2. Okay. So here is the formula. Here is the formula for the DFT. And now I will apparently complicate things. Rather than using the index n, I will use these two new indices. Okay. Again, to match the idea that now it's as if our signal is two-dimensional. We will do the same. So basically the second half of the trick, if you wish, is that we will take the index k and do something similar. We will write k also in terms of two indices, k2 plus k1 n2. K2 is from 0 to n2 minus 1, and k1 is from 0 n1 minus 2. And so what we'll do is that we will revisit the DFT summation, and we will write the DFT summation again. Now, again, what we did, as a summary, we replaced n is n1 plus n2 big N1, and k is replaced by k2 plus k1 n2. Okay? Where is this leading us? Now, when you do this, you will get this bracket multiplied by this bracket in the exponential of the DFT. So now this guy here, which we know from the definition of the DFT, now is written as such. Now we have four terms. So there is a term that is sort of, not harmful at all, which is e to the minus I 2 pi k1 n2 n1 n2 over n1 n2. These will go together, and this is equal to 1. But there are three terms. There are three other terms that are not equal to 1. So what we will do is that we will take those three remaining terms and we will write them in this form. Okay, so what is this form? Okay, again, it's just a rewriting, but it is a smart rewriting that will allow us to carry out the DFT operation efficiently. So again, write down your exponential, or your DFT sum doing this change. Take the exponential, split it into 4 parts. One of them is equal to unity. The 3 other parts will be split in this strategic way. Now focus on this blue term. So the blue term is so in this we have K2, N2. How do we obtain this one? We obtained it, so let me, K2, so there is K2 multiplied by N2, N1, divided by N1, N2, so N1 will go away, and you are left with this thing. So what is this summation? For a given N1, small n1, so if you think of this index as fixed, what are you doing? You have samples that are indexed by n2, and you are multiplying them by e to the minus I2 by k2 n2, and you are dividing by the number of terms in this sum. It's an n2 point DFT, exactly. It's an for every, so here, for every n1, and don't forget that n1 has this range, it starts from 0 up to n1 minus 1. For every n1, this is an n2 point DFT. Okay, and you can visualize it like you do the DFT of each row, right? Because I mean, if we go to the original array, what does it mean that you fix n1? It means that you are talking about a row. So what you are doing, like in this inner summation, this blue sum, it's compute the DFT of each row. And what is the size of this DFT? It is an n2 point DFT. So you will go to the first, so you take your data, you arrange it in the matrix, and then you take the DFT of the first row. You take the DFT of the second row, third row, you finish all the rows because you compute the DFT for every n1. Okay, so you will end up after the first step. You started with those small x samples. Now, what you have is that the first row will be the DFT of those samples, the second row is the DFT of those samples, and so on. Now, you multiply by this guy here. And before proceeding, note that when you do this, the index n2 is changed to k2, right? Because like you are summing over n2 and you get your result in terms of k2. The second step is that we will multiply by this factor here. Again, this factor is one of the 4 factors that you get when you multiply these 2 brackets. And so this is multiplication by, you multiply each, so your indices now will be n1, this is n1, and this is k2, and you simply multiply each element in this array by e to the I2 by k2 n1 over big N1 n2. Okay, so now once you do this step, so what do you have? So you have here something, okay, depends on n1 and depends on n1 and k2. What you do is that for a fixed k2, you compute the DFT of each column, right? So now the index of the column is k2, so you compute the DFT of each column for a fixed k2. Which means that you basically take the DFT of each column, and what you are left with is the original required n1 n2 DFT, but it is in a 2-dimensional form, but you can read it out, and now you read it out like this: x of 0, x of 1, x of 2 up to x of n2 minus 1, then x of n2, and so you read it row by row. You write it column by column, but you read it out row by row. How do we know that this is the DFT? Well, We know that this is the DFT because we started by nothing but the formula for the DFT. It is just that we rewrote the formula. What I'm computing is x of k k2 plus k1. I just replaced k by 2 indices, k2 plus k1 and 2. And then the summation that we have here is not an approximation or anything. It is the exact DFT sum. It is just written in a smart way by changing index n to n1 plus n2 big N1 and k to k2 plus k1 big N2, and then splitting the exponential and strategically thinking about the terms that we have. So the terms that we have can be rearranged so that you do the following. You do the DFT of each row, then you multiply by those guys, and then you do the DFT of each column, and then you have your DFT. You have the required DFT. So is this really efficient? Let's see. Remember that, the assumption, the underlying assumption is that you already have an efficient algorithm for DFTs of size N1, and you have another efficient algorithm for DFTs of size N2, and there is no problem if N1 is equal to N2 if you want to play this game with N1 equals N2. So let's suppose that the complexity of one N1 point DFT is given by this. So this is a constant. Typically, it's a small constant. And this is another constant. And let's alpha be the larger of these two constants. We will make use of it later. Let's basically track the operations and show that the algorithm we are talking about is actually order n log n. It is a fast Fourier transform. So you simply keep track of all the operations that you carry out. First step, you do n1 to n2 point DFTs because you take the n2 point DFT of each row. So the complexity will be this quantity here, which is the complexity of one n2 point DFT multiplied by n1, because you have n1 rows. Multiplication by the twiddle factors, basically you multiply the full array. Each element in the array is multiplied by this term here. Okay, so that's n1, n2 multiplications. And then we do the DFTs of the columns. So each column has n1 points and there are n2 columns. So the overall complexity is this quantity here multiplied by n2. Then you add an upper bound. Okay, so basically this is less than or equal to alpha, which is the maximum. This is less than or equal to alpha, and 1 is less than log 2 n1 n2. You can basically rewrite this bracket here. So you can you can have an upper bound on this bracket here, which is alpha plus 1 log n2 n1, and there is n1 n2 outside. Don't forget that n is n1 n2. That your number of samples is basically n1 n2, and so the complexity, the overall complexity, is proportional to n log n. So that's a wonderful idea, a very beautiful idea, that if you have an efficient, if you have a fast Fourier transform for size n1, and now you understand what does this mean. It means that there is an algorithm of order n1 log n1. So it's some constant multiplied by n1 log n1. If there is another algorithm that is efficient for data of size n2, so it means that the complexity is order n2 log n2. Now, can you combine them? Can you basically use those algorithms in some way such that the overall complexity of computing n1, n2, of computing a DFT of size n1 multiplied by n2 will be of order big N log n. Big N log n, yes. So this is the way to go. Think of your one-dimensional data as actually two-dimensional. Write it column by column. Do DFTs of the rows, multiply by the twiddle factors, do DFTs of the columns, and you are done. How do we know that this actually algorithm works? Well, we did nothing. No approximation, no bounding or anything. It's just a rewriting of the DFT sum. We rewrite it using two sums rather than just one sum. We try to think of small n and small k rather than as, basically two indices. We split n to n1 and n2. We split k into k1 and k2. And then you rewrite the DFT, and you will find that when you rewrite it, you will get this information. If you rewrite it this way, oh, this inner sum I can understand as fix n1 and take the DFT call with respect to n2. So this is a DFT of a row. Do it for all rows. Then multiply by the twiddle factors. Then do the DFT of each column, and you are done. Okay? So with Rader's algorithm, you have now the, almost all what you need to know about the efficient implementation of the DFT, basically for powers of 2, powers of 3, if n is composite. And Rader's algorithm will tell you what should you do if n is a large prime number. Okay. So this will be the end of the part on DFT. The DFT, of course, is a big and very nice topic, but it's like more expanded in a course on DSP. But for now, I mean, this is like for us basically the understanding of the DFT, its derivation from the DTFT, and its efficient implementation is basically the focus. And you will keep getting basically those DFT problems. And for the lectures, we will switch to convergence of random variables. Okay, no, we have something. I mean. Which again, it's like sort of a topic that will, it actually, you started basically doing this in your homework, the lasso problems and so on. So this is something again that, you will encounter it in the problem sets. So let's actually do it before going to convergence of random variables. It's the issue of sparsity. And sparsity is basically the idea that if you have a signal, there is a representation of the signal that is sparse. So if your signal is a real-life signal, most likely you can represent it in time domain or in frequency domain or using wavelets or whatever, such that in this representation the signal is sparse. So if you basically think of the signal as represented by a column of coefficients given some basis vectors, then most of those coefficients are actually 0 or negligible. And so what is the benefit of something like this? Your signal is compressed. Your signal is represented efficiently. So this is like a trend in signal processing. We do sparse signal processing again, in which we try to represent signals using basically some domain in which the signal is sparse. Now, if the signal is sparse in some domain, most likely it is very dense in another domain. So, I mean, if we just talk about time and frequency, a signal that is sparse in time is dense in frequency and vice versa. So we need like to understand this, this point, which is like, so what is the moral of the story? A signal cannot be sparse like, for example, the signal cannot be sparse in time and frequency at the same time. So there is like something fundamental that will prohibit a signal from being sparse in time and in frequency. So it is either sparse in time and you use its time representation, or it is sparse in frequency. How can we know something like this? Okay, so this is basically, this page is about this uncertainty relation for the DFT. Okay, and at the end I will tell you basically the inequality that that actually informs us that you cannot be sparse in both domains at the same time. Okay, so again, because this will answer the question that can the signal be sparse in something like the time domain and the frequency domain simultaneously, and the answer is no. Okay, let's basically take this. So there is a vector, a non-zero vector x, and this vector basically can be represented as a linear combination of the columns of psi or phi. Those are two unitary matrices. So if you wish, you can write x as psi alpha. So alpha is the representation of x using the columns of psi. Or, I mean, perhaps you prefer matrix phi, and beta is the representation of x using columns of phi. So it may be the case that if x is basically some time domain signal, perhaps psi's identity. So if psi's identity and alpha is x, which means that alpha is actually the representation of x in the time domain, but then you can take phi to be basically related to the Fourier transform. And so alpha and beta, one of them will be the time domain and one of them will be the frequency domain. Again, what is the objective of this thing, of this page, is to tell you that you cannot be sparse in both domains at the same time. It's a non-trivial idea, okay? But it needs to be demonstrated. Okay, so again, think of it as, and of course, like you can extend this to infinite dimensional signals. But here I will just talk about a vector of n samples, and you can write it in terms of alpha. So basically x is equal to psi alpha, and basically because psi is a unitary matrix, then alpha is equal to psi Hermitian x. Or you can write x equals phi beta, and in that case beta is phi Hermitian x. Because these two matrices are unitary, then alpha and beta and x, they all have the same L2 norm, which is non-zero because we assumed x is a non-zero vector. The all-zero vector, the all-zero vector is, it's the all-zero vector in all, basically representations, and so it's like an exception. But we are talking about a non-trivial signal here. We will denote the number of non-zero elements using this notation, and you basically studied this notation in one homework problem, and we know that the L0 norm is not really a norm, okay? But we write it as if it is a norm. So here is the idea. Take beta j. So beta j is element j here, okay? So from here we know, so beta is phi Hermitian x, and so beta j is the jth component. It is phi column j, which I denote as phi j Hermitian x. So write down beta in terms of phi and x. Now x can be written in terms of psi. So replace x by psi alpha. Now psi alpha can be written as a summation L from 1 to n, the nth column of psi multiplied by alpha n. Okay, so we can write down the jth element here in terms of this summation. Okay, now in this summation there are zeros in the alpha vector. You can remove the terms from the summation. If there are no zeros, you will not remove any term. If there are, if alpha L is 0, I mean, basically this summation without alpha L is as good as the same summation. So we have an equality here because we just remove the 0 terms. Then apply Cauchy-Schwarz inequality to this summation. Okay, and so it will give you this. So we'll apply the Cauchy-Schwarz to this term and that term. Okay, so we know that psi u, or let's say psi eta and gamma, okay, squared, this is less than summation magnitude eta squared multiplied by summation magnitude gamma squared. Now this summation with respect to L, this is the L2 norm squared of vector alpha. And then we have another sum that depends on phi and psi. Let's define the mutual coherence between phi and psi. Okay, so this is the definition, a matter of definition. So psi is a matrix with columns, phi is a matrix with columns. You define the mutual coherence as follows. You take each column, you take a column from phi, a column from psi, and you compute the magnitude of the inner product. And then the maximum magnitude of an inner product will be the so-called mutual coherence between these two matrices phi and psi. The idea here is that rather than having this summation, we will take all those magnitude squares and we will upper bound them by mu, by the mutual coherence. Okay, so the idea is that we will upper bound those guys by the mutual coherence squared, and then you have a summation, and this summation, it has how many terms? It has a number of terms equal to the number of non-zero elements in vector alpha, and so it is this quantity. So basically the idea here, why did people introduce mutual coherence? For a number of reasons. It's actually, mutual coherence is an important and useful concept, but using it here is basically this, that you have this summation, you want basically this quantity, which is a counter of the number of non-zero terms of alpha to appear. And so you will say, okay, let's just upper bound each guy here by the maximum possible value of the magnitude of an inner product between a column of psi and a column in phi. And so now you have this mu squared, and then you have a summation basically with a number of terms equal to the number of terms or the number of elements in alpha that are non-zero. Now sum both sides over j such that beta j is not equal to 0. So what you do here is that you take, basically you go from here to there, you sum j, beta j is not equal to 0. On the left hand side you get the L2 norm squared of beta. The right hand side is not a function of j. And so this is one benefit of upper bounding these inner products by the mutual coherence. So now, because the right-hand side is not a function of j, when it is summed, basically it gives you the number of elements in beta that are non-zero. Now, note the following. Recall that the L2 norm of x is the L2 norm of alpha is the L2 norm of beta. And so basically this guy and this guy are equal. And then you can write down that this product is greater than or equal to 1 over mu squared. And then by applying the arithmetic mean, geometric mean inequality, this is, we know that the square root of this quantity is less than or equal to the arithmetic mean. Okay, and then we take the square root, and so we get this very nice inequality. So, what does this inequality say? It tells you, suppose that you have a vector x. It has a certain representation using matrix psi and another representation using matrix phi. Now, the sum of the number of non-zero elements in alpha and beta, the representations using phi and psi, is lower bounded. It cannot be smaller than some number, and this number is related to the so-called mutual coherence between the two matrices. Okay, and you can actually compute mu squared if you choose one of your matrices to be identity and the other to be the unitary DFT matrix. So in that case, this right-hand side will be square root m. Okay, so what is the meaning of something like this? Suppose that you have a signal that is sparse in frequency, which means that its DFT is non-zero perhaps for 1 or 2 k values. So its DFT is non-zero for a few k values. Otherwise, its DFT is 0 or negligible. According to this inequality, its representation in the time domain must be dense, because the sum of basically the number of non-zero elements in alpha plus the number of non-zero elements in beta must be greater than or equal to 2 square root m. So if one of these two terms is very small, it must be the case that the other term is relatively large. Okay, so this is an idea. So again, the takeaway message is that signals, practical signals, are typically sparse in some domain, time, frequency, wavelet, whatever. And if they are sparse in one domain, one useful domain, they are typically not sparse in another domain. So it's useful to keep this in mind. Sparse signal processing is already there in your problem sets, and we will basically deal with it again. There will be a lecture in which we discuss in details the analysis of a famous algorithm called orthogonal matching pursuit. Okay, so stay tuned. Before I continue, next Tuesday, so there will be a tutorial session. Okay, so basically the third tutorial session this Tuesday, and it will be the study of important inequalities. So you use Cauchy-Schwarz, Jensen, Markov, Chebyshev, but we need like more powerful inequalities to prove some results in convergence of random variables. So you will basically study those in the tutorial session, and we will build on them in the lectures. Okay, so please, 5 p.m. you have this one, and it really saves you time if you attend and listen to the explanation. It's really much better to listen to someone explaining than to read the stuff yourself from scratch. Okay, so again, it's an advice. It is. Basically, this is the experience of many. Just reading it on your own, is not as efficient as basically hearing it explained. And perhaps discussing with the TA. Basically be interactive and discuss and ask. And as usual, there will be tricks in the proofs, and these tricks will appear. Some problems in the homework will be solved using these tricks. Like, for example, the trick in the proof of continuity of probability. Okay, so convergence of random variables. For motivation, please read the first couple of pages in the notes. Some of you already know convergence of random variables because they took AMCS 241. Others, perhaps this topic is not yet in 241 for those of you taking 241 in this semester. Okay, for motivation, I mean, why actually we bother about convergence of sequences of random variables? So please read the first couple of notes. I mean, it's related to many important things like estimation. Like if you collect observations to estimate some parameter, do you expect that your estimate will get better as you increase the number of samples? So increasing the number of samples is this business of computing the limit as n goes to infinity. So this topic, again, it seems very theoretical, but it is related to those practical concerns. Will you get better performance if you collect more data? And can you show it? Can you actually prove that things will be better if you increase the number of samples that you use in your estimation? Okay, convergence convergence of sequences of random variables, it comes with several flavors. In other words, mathematicians discover that you can define it. Mathematicians and statisticians, they discover that they can define it in a number of plausible ways, and all of them are useful. In several contexts. So, this may be like something, like sort of a burden, but, we need to accept it. Because again, there is a number of ways in which you can define convergence, because now your sequences are constructed using random variables. And so you can play with probability, you can play with expectation, stuff like this. So the first order of business is to keep in mind that convergence of random variables is not just a single definition. In fact, in this course, we'll have 4 definitions. And those definitions are related. They will look different, but they are related. And we will try to highlight basically how they are related. Our first concept of convergence is convergence in the rth mean. A sequence of random variables is said to converge to random variable x in the rth mean, and we write it as xn converges to x with an arrow and r, and it is understood that this convergence as n goes to infinity if each one of those random variables, it has a finite absolute rth moment. And more importantly, it must be the case that if you take xn minus x, which is the candidate, or which is the limit random variable, so xn minus x is a difference. Now, if you take the magnitude to the power r, that's sort of a distance. Right? We are measuring convergence. We are asking, is the sequence xn approaching x? So we need a measure of distance. And so this measure of distance, like in deterministic convergence, it can be done using the absolute value. So absolute value of xn minus x, and then we can choose to the power r. and then we can use R equals 1 or 2, or depending on whatever is more convenient in a certain application. But there is an issue here. The xn's and the x's are generally random variables. And so basically, how can we, this thing is sort of, it makes sense if, the x's are deterministic. Xn is 1 over n, is a deterministic function of n. But here, those are random variables. So how can we adapt this metric to the context of random variables? One way of doing things, expectation. So you compute this thing, but actually you compute its expectation so that you crush this into a number that depends on n, and then you need the limit as n goes to infinity of this to be 0. Okay, so to have convergence in the rth mean, we need this quantity to be finite for every n, and we need this expectation of the magnitude to the power r of xn minus x to go to 0 as n goes to infinity. Now, if you have convergence in the rth mean, there are 3 very important conclusions. The first conclusion is that if you have convergence in the rth mean, it must be the case that this is finite. So the rth absolute moment of x is finite. It must be the case. How can we show something like this? If there is convergence in the rth mean, it means that this limit is equal to 0. If this limit is equal to 0, it means that, as n gets large, this expectation is getting smaller. So there exists a big N such that this expectation can be made less than 1, because it actually goes, the limit goes to 0. Now, take expectation of magnitude x to the r, or to the power 1 over r, add and subtract xn, apply Minkowski, and so you can split this expectation into 2 expectations, one of them with x minus xn and the other with xn. Now look here, basically this guy is finite. Why? Why is this guy finite? Because each one of those moments it's finite. This is finite for every small n. And why this guy is finite? Because it is 1. Because big N is chosen such that this expectation is below 1, and again we are guaranteed to find this big N because we have this limit equal to 0. So we are upper bounding this by a finite quantity, so this quantity itself is finite. What else? Suppose that you have convergence in the rth mean. Automatically, you will have convergence in the qth mean, where q is a real number between 1 and r. So, suppose that xn converges to x with r equals 2, that xn converges to x, and you can put here any number between 1 and 2. You get it automatically. Why is this the case? It's a direct application of Lipinov inequality. So Lipinov inequality is basically, so this is Minkowski. So Minkowski is this inequality here. And Lipinov is this inequality that if P is greater than Q, then this expectation to the power 1, so this expectation raised to the power 1 over Q is less than or equal to this expectation raised to the power 1 over P, where P is greater than or equal to Q. So what is the relevance of this? Because Q is less than or equal to R, then this is less than that. So if you have convergence in the rth mean, we know that this is finite, so this must be finite. And this is an upper bound on that because Q is less than or equal to R. So, by the sandwich theorem, this expectation is greater than or equal to 0. So the upper bound goes to 0 as n goes to infinity. So it must be the case that this guy will also go to 0 as n goes to infinity. And so we have convergence in the qth mean such that Q is between 1 and R. So here something very important. For Q greater than R, we can't tell directly. So we can't, let's say we must check. Sometimes we have this, sometimes not. So if I tell you that there is convergence in the rth mean and R is equal to 2, so can we put R equals 2.5 or 3? Well, you need to check. Sometimes it will work, sometimes it will fail. What happened? For some reason, it stopped sharing. Okay. So, okay. Now, the last conclusion is that, and this conclusion, is not as intuitive as you may think. So, we have xn converges to x in the rth mean. So, here's the question. What about this? This is a deterministic quantity, right? So what you do is that you compute the, this expectation for n equals 1, for n equals 2, for n equals 3, and so on. So this is, in fact, a deterministic sequence. And then we can compute this expectation for x, which is the limit random variable, right? So basically the question is, does this converge to that as n goes to infinity? Question mark. So it turns out that if you choose Q to be less than or equal to R, then yes, you are guaranteed to have this convergence. Now, this is not true for other types of convergence, and I will talk about it. So, so for other types of convergence, let me actually write it. For of convergence, x add may converge to x almost surely. We'll talk about it later. But expectation xn may not converge to expectation n. Okay, so it is very tempting that you say, okay, so those random variables, they converge in some sense to a limit random variable. So, the moments, so the sequences of moments converge to the moments of the limit random variable. Wrong. Generally, this is not true. And convergence, for example, almost true convergence, by the way, is a strong notion of convergence. But you may have xn converging to x almost surely, and actually the moments, the sequence of moments is going nowhere. This sequence of moments may be going to 0, while this guy has a first moment of 1. Okay, so again, this is something that that you should prove for convergence in the rth mean, we can prove this property, and note that the proof is not for a general Q. So we are talking about moments with a Q that is between 1 and R. Again, if Q is greater than R, sometimes yes, sometimes no. The guarantee is when Q is less than or equal to R. Okay, let's do the proof. Okay, so note that we aren't sure that limit expectation xnq even exists. Who tells you that actually this deterministic sequence of expectations, those are numbers, again, for every n you compute this expectation, who tells you that actually you get a sequence that is even converging? We don't know. Okay, we don't know. So we will basically here, I will give you like an example of a rigorous proof in which you don't even assume that the limit exists and find the limit. We will actually, in the proof itself, show that actually the limit exists. Okay? Okay, so let's do this. Start with this expectation. Insert plus xn minus xn. Apply Minkowski. So you can split this into two terms by Minkowski. Take limit infimum of both sides. So let's do it. This guy on the left is not a function of a small n, so its limit or limit infimum or limit supremum is just itself because it's just a constant. What about the right-hand side? In the right-hand side, we have two terms. There is this term here. We are sure that the limit of this term, so again, this is the term in the definition. So we are sure that limit n goes to infinity is equal to 0 by definition, because we have convergence in the rth mean. So this, if the limit exists, so there is a theorem, if the limit exists, then limit infimum is equal to limit, and limit supremum is equal to limit. So basically, if the limit exists, then the limit infimum of this quantity is exactly equal to 0 because the limit is 0. Moreover, you have the limit infimum of this guy, and to be objective, you will just leave it as limit infimum because we don't even know whether this limit exists as you take n to infinity. Okay. Now start with this expectation. Insert the plus x and minus x. Apply Minkowski. Now take the limit supremum of both sides. Now for this side, you will just take the limit supremum, and you are stuck there because we don't even know. Limit supremum and limit infimum, they always exist as finite numbers or as plus or minus infinity. But the limit, if you have a sequence plus 1, minus 1, or you can have a sequence like 1, 2, 1, 2, 1, 2, 1, 2, it's not going anywhere. But limit supremum and limit infimum, by definition, they always exist. And so you will just leave this as limit supremum. What about the other side? We have two terms. This term is not a function of n, so actually its limit is itself, and its limit supremum is equal to its limit is equal to itself because it does not even depend on small n. This guy, it goes to 0 by definition because we are assuming that xn converges in the rth mean to basically x. So the limit supremum is equal to the limit, and this is 0. And that's our second conclusion. This is our second conclusion. Now, again, from your course on analysis, you know that basically limit infimum is less than or equal to limit supremum. If you don't know it, here I am saying it. You can show mathematically that this thing called limit infimum is always less than or equal to limit supremum. So this will allow you to combine both results, because you can now take these two guys, and since it's always the case that limit infimum is less than or equal to limit supremum, then you can write this chain of inequalities. This chain of inequalities is very nice, because you start with this expectation and you end up with this expectation, and this expectation is a finite number. How do we know? It's the first proof that basically if you have convergence in the rth mean, then the rth absolute moment is finite, and so any moment less than r will be finite. And so you start with something, you end with the same thing. So what does this mean? Every quantity that you see in this chain of inequalities is exactly equal. So limit infimum is equal to limit supremum, and so there is a theorem. If limit infimum is equal to limit supremum, then the limit exists. So in other words, there is a theorem in analysis that the limit exists if and only if limit infimum is equal to limit supremum. So you can show the existence of limit by showing that limit infimum is equal to limit supremum. And so the trick here was to upper bound the limit supremum and lower bound limit infimum by the exact same quantity. And so it means that it must be the case that limit infimum is equal to limit supremum, and so the limit exists. And what is the limit equal to? It is equal to this guy here. Okay, so here again, like you do the proof, and you know this is actually the correct way of doing things. Like you don't even assume that the limit, you show the existence of the limit while doing the proof, because who tells you, you know, if we have convergence in the rth mean, now if you compute those guys, who tells you actually that this deterministic sequence of expectations will even converge? We don't know, but now we have a proof. But remember that this proof is for Q that is less than or equal to R. Greater than R, you need to check. Sometimes you have this property, sometimes this property will be lost. Okay, any questions? Okay, one of the, you know, in many applications, people use R equals 2. And so this is called the mean square convergence. So mean square convergence is basically a special case of convergence in the rth mean, where r is equal to 2. And rather, sometimes you write it like this. You can write it like this. You can write it like this. You know, it depends on your taste. Let's take an example. Let xn is Bernoulli 1 over n. So basically, xn is 1 with probability 1 over n is 0 with probability 1 minus 1 over n. Now, do we have, so the question is, does xn converges in mean square to 0? And a comment here is that when I say that, for example, that this x is a random variable, it may be a degenerate random variable. So it may be a constant. So basically, our framework, it allows that, there is a random variable that takes a specific value with probability 1. Not a problem. So basically, this question is valid. So what is big X? Big X is equal to 0, right? So here I am saying, big X is equal to 0 with probability 1. Not a biggie. Okay, so, so again, don't be obsessed that, that a sequence of random variables may converge to a constant. May converge to a constant. You can say a constant, or you can say to a degenerate random variable, okay, to emphasize that by the end of the day, we treat those constants as random variables. Okay, so does xn converges in mean square to 0? Let's check. So remember, convergence in the Rth mean, you need to check two things. So you need to check this thing. Is this thing finite for every n? It's easy. What is the second moment of this random variable? It is 1 squared multiplied by 1 over n plus 0 squared multiplied by 1 minus 1 over n. That's 1 over n, and 1 over n is always finite. But the challenge now, is this expectation going to 0 as n goes to infinity? Well, you know, this expectation again is this 1 over n, and yes, it goes to 0 as n goes to infinity. So yes, we have convergence to 0. So that's an example of mean square convergence. So if you have a random variable x of x, it is equal to 1 with probability 1 over n. Okay, so basically x1 is equal to 1 with probability 1, but x2 is equal to 1 with probability 1/2. x3 is equal to 1 with probability 1/3, and so on. So this sequence of random variables converges to the degenerate random variable big X equals 0 in mean square. It converges in mean square. Okay? So, you will say that, how did actually you know that there is convergence to 0? You know, it is intuitive in this problem, right? Because, again, the probability that xn is equal to 0 is 1 minus 1 over n. As n gets large, the probability that the random variable is 0 like gets very, very, very close to 1. And so you may have this basically guess that perhaps, you know, there is convergence to 0. But there are some problems in which it is extremely, perhaps impossible to come up with a candidate limit, to have any sort of educated guess. So what should you do? What should you do if you simply, you cannot guess what is the candidate limit? How can you study convergence? This is a very, I mean, you know, no one asked me about it, but it's very annoying, by the way. In the definition of convergence, we say that xn converges in the Rth mean to x if, you know, if this limit goes to 0 as n goes to infinity. But I mean, what if you do not know x? And this is in many practical cases, we have no idea. You just have a sequence of random variables. So here's the good news. If r is equal to 2, so if we are talking about the special case of mean square convergence, you can check convergence without a candidate limit. Okay, so there are basically two criteria. So one of them is the Cauchy criterion. So it tells you there is convergence in mean square. So this is the special case when r is equal to 2. If and only if this limit, okay, so see this limit, it's different from the original definition. There is no candidate big X here. You just take xn and xm. So those are guys in the sequence. You take their difference, take the square, apply expectation. Then you take a double limit as n and m simultaneously approach infinity. If this is equal to 0, you have convergence in mean square to some random variable, even if you don't know exactly to what random variable we are converging to. So it's really cool. Okay, and again, like people, you know, in people who studied analysis, you know this Cauchy criterion. It is also for deterministic sequences in completive spaces, right? So sometimes you have no idea what the limit should be, but you can still study, or you can still assess whether a sequence will converge or not. Now, the proof of the Cauchy criterion is a bit advanced, and it actually requires that we study the other notions of convergence. Perhaps it's one of those things that we revisit at the end of the semester if we have time. Okay? Okay, so but let's apply it. So suppose I give you this problem. I give you this sequence of y's. They are zero mean independent random variables. They have a variance. The variance of yn is sigma n squared. Okay. So each y may have a different variance, and the sum of variances from 1 to infinity is a finite number. Okay. So here is the question: does the summation, so basically you can think xn is equal to this thing. So if you take the sum of the y's starting from 1 and stopping at n, does this converge in mean square? So basically implicitly as n goes to infinity. And this is a question: do you have convergence? Convergence to what? To some random variable. What random variable? You do not need to know. You do not need to guess. Okay, so that's basically the power of the Cauchy criterion. You can basically study this. You can give a definitive answer. Yes, I have convergence in mean square, without bothering about what the limit is. Okay, so for example, so in this problem, this is one type of problem in which the original definition of convergence is as useless as it can get. But the Cauchy criterion here is your friend. So do the Cauchy criterion. So take xn. Okay, so this is like xn, and this is like xm. Take their difference, square, and take the expectation. Now, after that, we will need to study basically the limit as n and m go to infinity. If it's 0, then we have convergence. So the difference between these two sums. So you sum. So there is a sum from 1 to n. There is a sum from 1 to m. Then the difference between these two sums is a sum from the minimum plus 1 to the maximum index. Okay. So we are summing, and then we are taking the magnitude square. Okay. And those guys are zero mean. And so what is this expectation? So, if there is a quantity and the quantity is zero mean, then its second moment is equal to its variance, right? So here we have second moment equal to variance, right? The variance of the summation itself, because the sum is zero mean. Now the y's are also independent, so the variance of the sum is the sum of variances. And what is the variance of each guy? It's just a given number, which is sigma k squared. So basically, and you can upper bound by, rather than having this as your upper bound, you can just upper bound by taking this to infinity. So this expectation is upper bounded by this summation that starts from the minimum of m and n, but the summation starting from 1 according to the problem statement. This summation is finite. So this summation is finite by the problem statement. So if you start it at a number and then you take the limit as this number going to infinity, then this sum will tend to 0. And you used this property in the proof of the Borel-Cantelli lemma. So because this summation is finite, then basically this will go to 0 as m and n go to 0. So this guy will go to 0. And so the Cauchy criterion is applicable, and we have convergence in mean square, despite the fact that we have no idea to the exact nature, the exact nature of the random variable to which we are converging. And there is another criterion, I will leave the proof to you, The other criterion, you can read its proof. You know, if you take the Cauchy criterion for granted, then you can basically do this proof. So the other proof, it tells you, rather than examining the difference between xn and xm, you do this thing here. You basically study the expectation of the product xn xm, the product of these two guys. You take the limit as n goes to infinity and m goes to infinity, and now you need the limit to be what? Not to be zero necessarily, but to be some finite number. So another way of assessing convergence is, other than the Cauchy criterion, it's something that can be more convenient in some context, is to study the expectation of the product and then take the limit, and the limit should be a finite number. Again, a friend of yours if you cannot make a guess regarding what is big X.